And I'm gonna draw on my screen here so people aren't distracted. I'll probably try to post it after maybe next week or something. Okay, thank you everyone for joining us. This is our 25th session of the quantum computing class at Hackaday. And this is also our 5th guest lecture. And I'm gonna do a very quick introduction of the class and Michael in a bit. This is our last class, actually. Welcome, everyone, and welcome back. Our season finale, where we spent since the last week of March, we've been having this class, and as you see, it's already been 25th almost every Sunday since the pandemic started. And kudos to everyone who's been coming to the class, and you've experienced a lot during the past few months. And we covered a lot of materials about quantum computing, from the basic concepts, physics, and to the algorithms, linear algebra, and also some hardware concepts. And today's class is one of the most interested topics, as we were discussing a lot of the previous concepts earlier. So I'm gonna introduce Michael in a little bit. So just for anyone who, every Sunday we have some newcomers. So welcome to anyone who's new, and this is the last class. If you missed anything, we have all of the recording and slides on the Hackaday project. So if you search on hackaday.io for comics on, quantum computing through comics, you'll find the recording of a topic that we discussed on Sunday. And we've been using the Microsoft Q# documentation as well as the quantum katas in our exercises. So we have some coding classes too. So as a lot of people know, since September, we've been having guest lectures, and we have 5 special topics. We covered cryptography, tomography, Q# communities project QTrill, and quantum machine learning. So today we have Michael Beverland, Dr. Michael Beverland, talking about quantum error correction. So Michael is actually my colleague at Microsoft. Welcome, and thank you, Michael, for joining us today. So Michael is a senior researcher at Microsoft Quantum, and he specializes in quantum error correction, a lot of end fault tolerance, and a lot of the questions we got during the past few months.
You can explain it mathematically, but
I'm going to mute whoever's talking.
Cool.
Yeah, this happens.
You're right, Mo. In a quantum computer, you can't create.
Someone's giving a lecture.
Say.
This is funny. Cool. Yeah, but today's lecture is Michael. So we'll be talking about quantum error correction. In the last few months, when we talked about measurements and hardware, we always had questions about how do we actually make sure what we are measuring are what we intend to. And by measuring, we also disturb the system. So how do we correct the errors that might be introduced during measurements? And Michael provided a very interesting abstract. So like in our everyday life, we don't see things like Schrodinger's cat in both dead and alive. So how is this affecting our observation due to decoherence? And how is superposition states being collapsed into any substates? So today's topic will be around that, and I'm very looking forward to Michael's lecture. And then just before everyone forgets, all of our class recording and slides are all posted on Hackaday, and also shortly after the class, it will be on my YouTube. And Hackaday also has a playlist that they are gradually uploading the past recordings. And of course, if you like anything physical, we have the book I published the book through making this class actually. All the topics except the guest lectures are all in this book. If you're interested, it's available in 13 markets on Amazon. And stay up to date. Even after today's class, we will have updates on Microsoft website. And some people are here due to the Microsoft Reactor promotions. And make sure you follow these meetup groups by the Reactor and sign up for their mailing list for their upcoming events. And when we have updates, upcoming events, or any new materials that we are introducing, we'll be posting them on the Hackaday project. So definitely follow that. And a final reminder of the MS Learn modules that Microsoft produces for you to get hands-on with quantum computing. So check out these links. I'll be posting the slide with the links on Hackaday after this. And of course, the usual suspects of the social media posts if you want to see anything right when they're published. All right, thank you, everyone. Let's welcome Michael.
Hey everybody, thanks a lot, and thanks Kitty for the introduction. And yeah, it's really cool to be a part of this project. It's something that I think is really awesome that you've put together, and it's an honor to be the final speaker of the series. So that's great. I'm just going to share some slides here. So that'll take just a second. Okay. So as Kitty mentioned, we're going to be talking about quantum error correction, and I do think that the big picture way to think about this is really, you know, you've all heard of Schrodinger's cat and about the bizarre quantum effects that exist in the quantum world, but quantum mechanics is what we believe, or our best understanding of how the universe really works. And so why is it that we don't see these quantum effects in our everyday life? If that's what's going on at a fundamental level, why are we not experiencing quantum superpositions like Schrodinger's cat? And moreover, this quest that we're all along to build a functioning, scalable quantum computer, in some senses, is like building Schrodinger's cat. We want to, you know, we know that quantum mechanics is how things work at a small scale, and indeed you need quantum mechanics in order to be able to predict behavior of atoms and molecules. But what we want to do is we want to build a huge quantum system which exhibits these same quantum effects unspoiled. And of course, the reason that we don't see these giant superposition states, and we don't see these entangled properties that we have at the small scale of quantum systems in the everyday world, the reason for that, of course, is that decoherence is happening. And that's really what we want to prevent with quantum error correction. So today I'm gonna talk through the big picture of this field, how we think about things, some of the strategies that are used to protect information from noise, and to build out a large-scale quantum computer. And I'm also gonna, because this is the last in a series of different topics that Kitty has covered and other guest speakers, I'm going to assume a fair bit of knowledge, but I'll try to not assume any of the standard topics in quantum error correction. Also, if there are any points where people are confused, then I don't know exactly what's been taught in the previous classes as well. So if there are things which I'm assuming, which I should not have assumed, feel free to jump in and ping me and ask a question. Okay, so the basic idea of quantum error correction is encapsulated in this picture. We know that these qubits that we have, which are represented by black circles here, or black disks, are going to be noisy, which is represented by these little blue clouds around them. And so the idea is that we're going to hope that we can, accept they're going to be noisy, but we can hope that we can somehow get a large number of them, and using a large number of noisy qubits, trade that for a single, much less noisy logical qubit. And then the logical qubit is what we will run the quantum computer on. And so the point is that the number of logical qubits will be less than the physical qubits we start with, but of course the probability of each of those failing will also be less, and that's why we would do this. So you can think about it a little bit like an emulator for a computer. If you grew up with some old computer console that you want to use today on your regular computer, and you can emulate that on your regular computer. And in some sense, what we want to do is, with a large number of physical qubits, emulate a perfect qubit. So how perfect does it need to be? Well, the encoded information doesn't have to be absolutely perfect. It just needs to be good enough so that for the particular quantum algorithm that you want to run, it will succeed with high probability. So what you can imagine is, suppose the quantum circuit that you want to run, maybe it implements Shor's algorithm or something else. Suppose it has a certain set that consists of a number of qubits and a number of operations. So you can think all of the operations that happen in this entire computer, we can think of as the circuit size. And what we want is that with reasonable probability, none of those different pieces of the circuit will fail. This is going to be satisfied, roughly speaking, if the probability of each component failing is at most 1 divided by the total number of things in the circuit. Then probably nothing will go wrong whenever we run it. This is just a back of the envelope way of thinking about it, of course. Okay, so something before we get into the details of this is I want to mention two terms: error correction, quantum error correction, and fault tolerance. And these terms are often interchanged whenever you read about things in popular media, and also, in fact, often interchanged whenever you read about things in quantum error correction, in quantum computing articles that are not focused on quantum error correction specifically. And I just want to highlight that these things are a little bit different from one another, and we'll come back to this later. But quantum error correction is kind of an ideal setting, and it's where we come up with toy models, essentially, for what we really want to do. Fault tolerance is really what we actually want to build. We want to build quantum computers that are fault tolerant. And just as a rough idea of what the difference between these two things are, if you're familiar with the more computer science way of thinking, quantum error correction is a little bit like an oracle in computer science, where in fact you imagine that you have some extra power that we don't really have in the real world to measure things perfectly. And so we can measure perfectly different parts of the physical system and use those measurements to learn about noise which has occurred. However, just like oracles in computer science, in reality, we don't have that power. And so what actually we need to do is have fault tolerant schemes to find out about noise in the system, where the process that we use to identify the noise can also go wrong. And that's really what we need. But anyway, don't worry too much if this didn't make a lot of sense at this stage. We'll come back to that later. Okay, so what's the rough idea? So let's think about the non-quantum case first. So you can, of course, imagine a scenario where some information needs to be sent from one place to another, but there's going to be some noise which occurs, which causes the information to be corrupted. For example, imagine if you have a space probe, and as it gets further and further from Earth, the signal becomes weaker and weaker, and then every time the space probe wants to send back some important scientific data to Earth, there's a possibility that that information will be corrupted. So a simple model is that the probe sends you ones and zeros, which encode the information, and that each of those bits that it's sent could be flipped with some probability p. So what's the solution to this? Well, a simple solution that you probably already thought of is, instead of sending a single bit for each bit of information that you want to convey, that the space probe wants to send back to Earth, send a repeated set of bits. And then, so for example, instead of sending 0, send 0, 0, 0, and instead of sending 1, send 1, 1, 1. And we can call the bits that we send physical bits, and the bits that we actually want to convey the message logical bits. And this will have a parallel with the quantum case later. So how does this work? Well, of course, the receiver might receive 0, 0, 0 and identify that the message that was supposed to be sent was a 0, but it also could receive 0, 0, 1. And that would be interpreted as the third bit that was sent was flipped. But then, of course, it would be identified as the intention being sent was a 000 with a bit flip. And so you can work out the probability of still getting the answer wrong, even though you're encoding information in this way. And of course, you can get things wrong whenever 2 bits flip. And so that does happen, but it happens with lower probability provided p is relatively small. So for example, if you had p being about 1%, then the probability that there would be a logical failure would be about 30 times less than that. So you indeed gain from this. And if you want, you can make it even better. So you can, instead of using 3 bits instead of 1, you can use an arbitrary number of bits instead of 1, and do the same thing, and you'll get a lower and lower probability of things going wrong. So here I've just shown a curve of the probability of a failure. The probability of a failure whenever you have the probability of a logical failure of your message whenever you have some probability of a failure on the x-axis of the actual bits, each bit individually. And if you want to get a really accurate final result, then the overall probability of 10 to the minus 10, for example, then you might need hundreds or thousands of bits to encode that information given these values of p here. And if you want even more accuracy, then of course you need more bits to encode that information. So this should all make rough sense. There's one point here that I want to point out where if each bit is flipped with probability 1/2, then you're really beyond hope. There's no way of encoding any information in that case. Okay, so what about the quantum case? That was all for this non-quantum case. So there are some challenges that were clear at the outset of the field of quantum computing, and actually led many people to believe that quantum computing would never actually be possible or practical. And the first one is that it's not the case where, whereas this scenario we were describing before was for a satellite that was, or a space probe that was moving further and further from Earth. So there it seems that the classical information needed protected because it was getting weaker and weaker. In the quantum case, we don't just need to protect the quantum information in very contrived scenarios of elevated noise like that. We actually need to protect the information all the time. And part of the reason for that is that there's just more that can go wrong for the quantum system. So for example, if you have a quantum state, which is alpha 0 plus beta 1, so this is an arbitrary single qubit state, then there's a huge number of ways that this could go wrong. In the classical case, if you have a bit, which is 0, then it could be flipped to 1 or not flipped. And those are the only two possibilities. But in the case of the quantum state, then it can change, alpha and beta can change by an arbitrary amount. Or you can have something like just a phase change between the two. So it doesn't change the overall magnitude or the overall probability of measuring 0 or 1, but it does change the state. And so there are many, many ways, an infinite number of ways, in fact, that a quantum state could be corrupted by noise, whereas there's only one way that a piece of classical information could be corrupted, by being flipped. The other thing is that measuring the system destroys the state. So it makes it hard to imagine a scenario where we can somehow make sure that errors have not occurred or fix errors as we go, because if we want to check the system, then we're going to need to measure it, and we know that in quantum mechanics, when we make measurements, we collapse the state. So that seems difficult to get around that. Another thing which is even more fundamental is that if you have an arbitrary quantum state, then you can actually prove, just using the rules of quantum mechanics, that you can't copy it. So we can't do something like we did before, where we take a 0 and replace it by 0, 0, 0, etc. For the quantum case, because if we have some arbitrary quantum state like alpha 0 plus beta 1, we can't just copy that. It's impossible. Okay, so this all seems like bad news, but these problems can be overcome, and it's remarkable that these problems were first overcome and pointed out by Peter Shor, the same researcher who discovered the algorithm for factoring, which really kicked off a large amount of progress in the field of quantum computing. It was also at a very similar time. I think it could even have been the same year in the 90s. Okay, so the point, and I will come back to this later with some examples, but the point is that we use entanglement to protect the information. And instead, so for example, each of these little disks here represents a qubit, and instead of encoding the information in one of those disks or copying it among the others, we actually encode it in the entanglement degrees of freedom between these different qubits. And it's not obvious why that works right now, but what we'll see later is if something happens to just one of those, then it doesn't destroy that encoded information. It can be perfectly recovered. Another key thing that we'll see later is that what we learn whenever we check the system is we learn about the errors. So we will end up collapsing the state of the system in some way, but not completely. We won't collapse the part which encodes the information. We'll just collapse the part which encodes the error. Okay, so here is a similar picture to what we showed before. Although those of you who are paying attention will notice that the x-axis in this case for the quantum scenario is in the logarithmic scale, whereas it was linear scale in the case for classical information. And that shows that things are a lot harder in the quantum case, but they're still possible. So with quantum error correction, with some well-known approach, this graph is plotted for this. You can achieve something very similar qualitatively to what you achieve in the classical case. If you want to store information with some specified logical error rate, like 10 to the minus 10, then you can do that with a large number of qubits. And of course, the number of qubits that you require depends on the probability of each qubit failing. And of course, if you want more accurate stored information, then you're going to need more qubits to do that. But something that I just want to point out here is that it's important to note that if your qubits are better, if they have lower noise, then you need far fewer of them to do so. So for example, if the probability of failure is 10 to the minus 3, which is roughly what the superconducting qubit approaches are aiming for, then this is kind of the ballpark using this particular approach of the number of qubits that will be needed to store a single logical qubit, number of physical qubits per logical. But using that same approach, if you manage to achieve a much lower error rate, which could be possible with, for example, the topological approach, then you might need far fewer qubits. And the other thing I will point out is that there's also a threshold here, like for the classical case, and it's much lower. The classical case was a 50% error rate was the threshold. Here it's 1%. So if your qubits are not better than that, then error correction is not going to help you. Okay, so this is one of the reasons that we believe that it's very important when describing how far an experimental team has gotten with their quantum hardware. It's not enough to report how many qubits they have. It's really important to know how good they are too. Okay, so how does this work? Well, let's first of all remind ourselves about some of the basics of quantum mechanics as they're relevant to this topic. So suppose you have one qubit and you measure it. Then as we know, you collapse the state and you collapse the state completely. So if you have an arbitrary quantum state over 0 and 1, then in this particular case, when you measure it with some probability, which is the modulus squared of the coefficient in front of the 0 ket, then you'll get a +1 outcome, and with some other probability, you'll get a -1 outcome. Okay, very good. Another thing that I'll point out here, I don't know if you discussed, is measuring z here. So this just means that we're measuring in a particular basis. You could measure in another basis. So we're measuring in the 0, 1 basis. You could measure in another basis instead of that. which is important for quantum error correction. Okay, so what about when you have more than one qubit? Well, if you measure, then it's possible to only partially collapse the state. So for example, suppose you have this arbitrary 2-qubit state here. So now there are 4 complex coefficients, A00, A01, etc. And let's suppose that we just measure the first of these 2 qubits. So that means that we are going to collapse the state of the first qubit, but not the second. So what happens in that case, and this may not be familiar to people, and it's not discussed as often, but what happens is that you will end up after this measurement with still a superposition state, but the superposition will only be over the second qubit. So look at this state here. Notice that both parts of it after the measurement are in 0 for the first qubit, whereas the second qubit is in a superposition. And so the superposition survives for the second qubit, but not the first. And that's only if you get the +1 outcome for your measurement, because we observed a 0 state for the first qubit. And that happens with this probability, but don't worry too much about the probabilities right now. And you could have also gotten a 1 for that, and that would have happened with this other probability. Okay, so that's one thing. And before we go into a little bit more detail here, I want to just think at the conceptual level of what's going on. Of course, it's true that if you have 2 qubits and you measure one of them, the other one's going to survive in some way. For example, if 2 different experimental teams have 2 completely independent qubits, and one team is working on their qubit and the other team is working on their other qubit, then it must be possible for the teams to independently address their qubits and for things not to go wrong because of that. So we know that in a very kind of trivial case, whenever 2 qubits are completely independent, that measuring one will not collapse the other. Here we're showing a case where the qubits are entangled in some way because these coefficients are arbitrary, so we'll include some cases where the qubits are entangled. But it's still the case that you don't completely collapse the system whenever you just measure one of the 2 qubits. So another example that you could measure is instead of measuring just one of the 2 qubits, you could measure something else which still gives you a bit of information, but it's not the same thing as measuring one of the qubits, and that's the parity. So imagine measuring the overall parity of these qubits, and that would mean that if the state is 0, 0, that has a parity +1. If the state is in 1, 1, that has a parity +1, 2. But if the state is in 0, 1 or 1, 0, that is a parity -1. So all we mean by parity here is just it distinguishes modulo 2 the sum of the entries in a bit string. Okay, so again, this will collapse the system partially, but not entirely. So if you get a +1 outcome, then it will collapse into this combination, this superposition of the 0, 0 and the 1, 1 parts of the state. Whereas if you measure a -1 parity, that will collapse into the other 2 parts of the state. But again, the outcome is the superposition. So the goal of QEC then is going to be to store our information in specially chosen states, so that whenever we do measure certain things about the state, we will learn about the error, but not about the information that's stored. And let's, in fact, use a particular example to see how this might work. So we suppose that we're going to make a lot of assumptions here because it's going to be a very simple example, but the concepts are going to be the same as for the more general cases. So suppose we have a state alpha 0, 0 plus beta 1, 1, and we don't know what alpha and beta are. They're completely arbitrary. This is an arbitrary quantum state. But note that this is a quantum state on 2 qubits, and it's not completely general because we don't have there's no part of the state which is in 0, 1 or 1, 0. And that will be important. And suppose that we are told that there's only one possible error that can occur. Either an X is applied to the first qubit or it's not. And our goal is going to be to come up with an error correction scheme for this scenario. So if we we're going to measure something, and then depending on the outcome of that measurement, we're going to do something to fix a potential error that may have occurred. So in this case, the thing that we do is we measure the parity. Let's see how that works. So there are two cases. Of course, we don't know which one of these cases has happened, but one of the cases is that nothing's happened at all, and then of course we're in the same state as we started with, alpha 0, 0 plus beta 1, 1. And if we measure the parity in this case, we get the outcome plus 1. And that, of course, occurs with certainty. If, on the other hand, this x error has happened, well, what does this x1 do? As we know, it flips 0 and 1. So the state, given the x error, given the x1 error, will be alpha 1, 0 plus beta 0, 1. And if we measure the parity of this state, of course, we get the minus 1 outcome. And that's with absolute certainty again. If an x1 error has happened, then we will definitely get a minus 1 outcome for this parity measurement. And so then our correction procedure should be, after we've measured the parity, if we get plus 1 parity, don't do anything. And if we get minus 1 parity, flip the first bit. So apply an x1. And that will recover the original state. So this is an example where we learned nothing and we didn't collapse anything about alpha and beta, but we did learn about whether an error had occurred or not, and we know how to fix it. So that's a very simple case. And this is a point where if I was giving this talk in person, I would be looking at people's faces to see how happy or how confused they are, because I'm going to go into more detail. So if somebody wants to chime in and say that maybe we should skip a more detailed example, now is your chance to do that. I'm going to wait 10 seconds to allow.
There is a question in the chat for an earlier slide. I'm not sure if it's completely answered from your. Yeah. So Thomas asked, what do you mean by fail? So one earlier slides you use the word fail. The amplitude are continuous. Doesn't a qubit kind of always fail?
Yeah, I think it's a good question, and it has to be carefully defined, but it's very well defined to say fail for an overall quantum computation. So you have some quantum computer, you set it up with some initial input, which is just classical information, right? You start your computer by inputting ones and zeros, there's no superposition. And then you run your quantum computer, which builds superposition and does lots of complicated things. But at the very end of your quantum computation, you measure all the qubits and you get some output, which is, again, some classical information, just a bit string. And at that point, it's possible to understand exactly what a fail means. For example, if you're running Shor's algorithm and the input is encoding an integer to factor, and the output is encoding a pair of integers which are supposed to multiply to give the input. If that's not the case, if the output does not multiply together to give the input, that's a fail. So failure is well defined for the entire quantum computation, and it really just means has something gone wrong during the computation. And then a slightly more blurry thing, but that we can still define, if we're careful, is the failure of a component within a quantum computer. So we can understand that something somewhere in the quantum computer has gone wrong. I don't know if that satisfactorily answers the question or not.
Thomas comments, so it's a probabilistic fail?
When a failure occurs, yeah, I think it's a hard question to answer in a really clear way. So the failure itself will be probabilistic, but when a failure has occurred, when you use your quantum computer, it either will have occurred or not. From the outset, it will be probabilistic. If you run the same quantum computer again, it might not fail the next time. But yes, it's when you run it, it definitely has failed, or it definitely has not failed. But if you run it multiple times with the same noise processes acting, you may get sometimes it fails and sometimes it does not.
Great, thank you. I have a quick question here. Hopefully it's quick. So how do you even measure and get these parity +1 and -1?
Yeah, so depending on how much time we have, we will come back to that a little bit. But just as a rough idea, you build a gadget. So you have some allowed things that you're allowed to do in your hardware, and it depends on the hardware that you're using, what those allowed operations are. But these actions of measurement you build them out of those basic building blocks that you're allowed in your hardware. With Majorana qubits, for example, actually measuring parity is a direct operation. So if you have two Majorana, if you have two qubits encoded in tetrons, for example, built out of Majoranas, and they're in neighboring patches, then you can just directly measure the parity of that pair of qubits encoded. But in other hardware, there's like different things. There's different ways you do that.
Cool. Let's go forward with these and come back to additional questions if we have more time afterwards.
Okay. Sure.
Thank you.
So what I want to walk through now is at a very high level is how you do error correction when you have a slightly more realistic scenario for noise. So the first thing is now we're going to have 7 qubits instead of 2, and we're going to encode 1 qubit among those 7. And we're going to have to make some assumptions here because we don't have time to go through all of the theory carefully. But the point is we're going to have 2 states which satisfy certain conditions in the space of this set of 7 qubits. So in principle, there's actually an overall space of 2 to the power of 7 here, but we're going to choose 2 states within that very large space as our code states. And those 2 states are going to satisfy some special properties. The first property is that if we measure the parity of any 4 qubits, so for example, I think you can see my mouse here, if you take the 4 qubits around this face at the top, then if we measure the overall parity of those 4 qubits, then in both of the states that we are going to encode our information in, we'll get a +1 outcome. And the same thing is true of these 4 qubits in this face here, and the same thing is true of the 4 qubits in this face here. Okay, so those are 3 conditions on these states. There's also another 3 conditions, which is if we measure the X parity. So what this means, we don't need to worry about this too much if it's not something that you guys have covered, but instead of measuring the operator Z, 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 we can measure the operator X, 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 X. But it's really the same thing as checking the parity, but in a different basis. And again, if we do that for the 4 qubits in this face, we'll get a +1 outcome on those states. And if we do it for these, we'll get a +1 outcome. And if we do it for these, we'll get a +1 outcome. Okay, so now let's talk about what happens if we have an error. So an X-type error, if an X-type error afflicts a single qubit, it will cause any of the Z face measurements to flip that touches that qubit. So instead of getting a +1, which we would get for these special states that we encode the information in, we would get a -1 for a face which touches that qubit. And so we can just walk through the cases of different qubits. Suppose there's an X error on this qubit here, then because these faces over here don't touch that qubit, they will have a +1 outcome. They'll be satisfied as we expect. But this face here, because it does touch that qubit, will be flipped. So we'll have a -1 outcome for that parity measurement. And that pattern of good, good, bad will identify this qubit as the one which has the X error on it. And just by rotating this, you can imagine that you would identify this qubit here or this qubit here as in the same way. And what about instead of these corner qubits, if we had one of these edge qubits, then of course there will be 2 faces which have their parity measurement flipped. Both of these touch that qubit. And of course the other 2 edge types would be identified in a similar way. And the last one is if the middle qubit has an X-type error, then we can identify it as well. And so if any single qubit is afflicted by an X error, then this qubit or this code will tell us what qubit it was. And this is better than the previous case because it only told us what happened if the first qubit had an X error. But if the second qubit had an X error, then we would actually be in trouble. We would have gotten a -1 parity measurement, and we wouldn't know how we wouldn't fix it correctly. We would actually introduce an error. But here, in this case, we can identify uniquely all of the single qubit X errors. Moreover, by measuring the X-type parity, we can measure single qubit Z errors. And just by symmetry, it's exactly the same. If we have a Z error on this qubit, then the X parity will be flipped for this face, but not the other two, etc. So we can measure, we can identify and then fix by applying the appropriate correction all of the single qubit X and Z errors. And importantly, the Y-type Pauli operator is just the multiplication of an X-type and a Z-type Pauli operator up to some overall phase. And we know that overall phases don't actually matter in quantum mechanics. If we multiply a superposition state by a global phase, it doesn't actually change the state. So we don't care about this little square root of -1 here in front of the X and the Z. So by separately measuring the Z-type parities and the X-type parities and correcting the the X-type errors and the Z-type errors, we actually automatically, without any extra effort, will correct the Y-type errors as well. So this can correct against any single qubit X, Y, and Z error. And another thing that I didn't go into any detail on here, but which is really beautiful and important, is moreover, even if each qubit has some superposition of different types of error, so instead of just an X error or a Y error or a Z error, it actually has some superposition of those. Whenever we measure these different operators, these parity operators, it actually collapses into one of these three cases. And this is the beautiful way that quantum error correction solves the problem of having an infinite number of different types of error, because the measurement that you use in quantum error correction actually collapses into a finite set of errors. Okay, so this, the code that I just described, this approach to quantum error correction, was actually a famous code called the Steen code, but it's the first, it can be viewed as the first instance in a family of codes. And it was able to correct against a single error, but when you generalize it, you need more qubits, but it can correct more errors. The second one can correct 2 errors and then 3 errors, etc. And you can make it as big as you want. And the point is that you can, by making it bigger and bigger, you can get better and better protection against error. Although you're paying for it because you need more and more physical qubits to encode just one logical qubit. Each of these different versions just encodes one logical qubit. So the picture over here shows that the value P of each error on each qubit on the x-axis, and then the probability of an overall failure. And so what I was describing was you get better and better protection as you make the system bigger and bigger, as you increase this the size of this triangle, and therefore the number of qubits that you need. But there is a trade-off, there's a crossover point. If the noise on each qubit is too high, then you actually make it worse. And it's kind of clear to see where this comes from intuitively, just by the fact that if you have a larger number of qubits in your system that you're using for error correction, there's more things that can go wrong. So even though you can correct more errors, more can go wrong as well. And you win this trade-off if you're below some particular threshold value of the noise. And that's what I was talking about when I talked about threshold before. It's this turning point where below which things are getting better with error correction and above which you shouldn't use error correction at all because things are going to get worse. Okay, and I just wanted to flash a picture of, we had one particular family of strategies, we can say, for quantum error correction, but there are many. And there are many which are being invented all the time. And it's very exciting that that so much work is being done in this particular area, and it's something that this is my research area, so I'm very passionate about these new developments which we are making all the time. And then I just wanted to highlight, we alluded to this earlier, what happens whenever we go from error correction to fault tolerance. So here we said we could measure these parities and that will tell us about errors that occurred. But as Kitty brought up, we need to think about how do we measure these parities. In the first contrived example where we just measure the parity of 2 qubits, that might be possible in some systems like in Majorana systems, but not in others. And in a scenario where we have a bigger error correction scheme, like for the Steen or the color code as I described in a little bit more detail afterwards, then we need 4 qubit parity measurements. And how do we do that in practice? Well, the fact is that we need to build these from some basic operations that are actually possible in the physical systems. And those basic operations can go wrong too. So maybe we actually introduce errors when we're trying to find and fix them. So just as a rough idea of this is a circuit built of smaller pieces, which allows you to measure the X-type parity. So here, each of these wires represents a single physical qubit, and the goal is to measure the X parity on all of those. And a gadget to implement that measurement is this one. We introduce one additional qubit here, an ancilla one, whose job is really just to help us with this measurement. And we prepare that qubit in the plus state. We apply control NOT gates from that ancilla qubit to each of the qubits that we want to measure the overall parity, X parity of, and then we measure that qubit. And that outcome, if nothing has gone wrong, if there's been no faults in this, will tell us the overall parity, the X parity. But of course, each of those things might go wrong. And so whenever we have some circuit like this, we replace each piece of the circuit, as I've shown here. This is some other circuit, now not necessarily for measuring a stabilizer for error correction, but just some arbitrary circuit. And each of the pieces in the circuit should be considered noisy. So what do? Is we follow, whenever we're simulating and imagining how this works, we make a noise model where we follow each of the components by some error event that is possible. So for example, a Hadamard gate would be represented in this picture, this noise picture, as a perfect Hadamard gate followed by some probabilistic process where you apply an X or a Y or a Z with each with probability P over 3. But anyway, this is getting very detailed, but the idea is that what we described before was very contrived, and what we really want to do is much harder. And so I'm not going to go into detail on this, but the idea, there are strategies to deal with this, and they're known as fault-tolerant error correction. And one of the ways that we can achieve this is to have to repeat measurements and use the fact that we now have some repetition in the information that we've gathered about the errors in the system to be able to trust that information better. Okay, but one thing I want to point out here is that the current best approach in some regards is the surface code, and you've probably heard about that before. And the surface code has a threshold for quantum error correction given noise in the measurements of around 1%. And it's important to point out that before that, things were continually getting better, but the original thresholds, the early thresholds that were discussed in other types of approaches to quantum computing were much, much lower, so much harder to achieve with hardware. So instead of 10 to the minus 2, they were 3 orders of magnitude lower than that, around 10 to the minus 5. And no hardware that people have today at scale, well, I should be a little careful with what I say. It seems very improbable to me, at least, that at scale you can get much better than that kind of threshold. And if you're not considerably below that threshold, then I think, yeah, quantum error correction wouldn't be able to work at all. And the point I'm trying to make here is that advances in just the theory of quantum error correction and fault tolerance can take things which are available in the lab from not being possible to make scalable quantum computers out of them to it being possible to do so. Certainly that's what happened in the case of going from the original approaches to the surface code. Okay, another thing that we look at and we think about a lot in this field, but I'm going to skip, is how you implement gates on the logical information that's encoded. But there are ways of doing this, and some of these gates can be very costly. And in general, for example, typically quantum error correction approach will allow some gates to be implemented quite easily and some other gates to be implemented in a really difficult way. And in the surface code, for example, the Clifford gates tend to be quite direct to implement, but the non-Clifford gates can be very costly to implement, and you actually use something called magic state distillation to do that, which I'm not going to go into in detail. Yeah, so I think I'm going to skip the details of this part so that we have some time for questions, if there are any. But the point is that it's not just enough to store information fault tolerantly, you also need to be able to process it. And this is a quick sketch of how magic state distillation works, but this is essentially the most costly of the operations that you would perform, for example, in the surface code. And the reason it's so costly is because it's not a natural gate, and you need to build it out of many, many, many smaller gates, and use this process to take those small, noisy operations and make them into large, clean operations. But that process requires a huge number of inputs, and so it's very costly in a quantum computer. Okay, so let me skip. Yeah, okay. Let me skip that and just go to the summary. So the things that I described and want to highlight are, first of all, that noise is one of the main things that has held us back from scalable quantum computers. Quantum computing was first proposed in the 80s, and people have been working hard to make it a reality, and we're getting very close to scalable quantum computers today, we believe. Feel that we're on a precipice at this moment, but there's quite a period of time between then and now, and one of the major challenges was overcoming the effects of noise in quantum systems. But we have been able to achieve that, and so there are quantum error correction and fault tolerance schemes that have been designed that will work if we have good enough qubits and if we have enough of them. But those existing schemes are still much more restrictive than we would like, and we would like to have new ones which allow us to use systems which don't have to be quite as good and where we don't need quite as many physical qubits per logical qubit. And as has happened before with quantum error correction, if we have new ideas and new approaches, then these approaches, without actually having to change the hardware that exists, could jump the field forward by many years. So I think I will end there and switch over to questions if there are any.
Yeah, there are a couple of questions in the chat. So one at 9:06 my time. What if there are multiple devices with same initial condition for copying states, so failure part and parity bit?
Can you repeat that? What if there are multiple?
Yeah, I'm just reading. I'm not quite sure
Yeah.
what they're asking actually.
But read it again. Maybe I can figure out what's meant. Or can I see? I don't actually.
Yes, you can see the message too. So that's when we were talking about fail.
Yeah.
And Sumit asks, what if there are multiple devices with the same initial condition for copying states, so failure part and parity bit?
Yeah, so I think I'm not totally sure I understand the question, but the problem is that you can't copy a quantum state. So what I imagine this person is thinking about is, what if you just start two completely different quantum computers, and you start them in exactly the same way, and then you then you know that after a certain period of time, you're going to have the same state, if no errors have occurred, the same state in each of them. Then can you somehow use this information to help you? And the answer is not in a really scalable way, because the things which are going to happen separately is going to be different in the two cases. So yeah, there'll be different errors in each of the two systems that you run, just because, as we discussed, they're probabilistic. So in one case, there'll be one error, in another case, there'll be a different error. And eventually, for a big system, those are going to build up into the completely separate sets of errors that you can't use to check across one another. And you wouldn't be able to, yeah, in the classical case, you can just copy your state, and you know that any errors that have occurred between the two copies, so any discrepancy between the two copies happened either during the state being copied or since then. But in the quantum case, you can't do that. You can't just copy your state at a particular moment. So yeah, that's one of the problems.
Yeah. And another question from PK, can repetition of an experiment to come up with a result based on probability?
Yeah, so again, I think this is a similar point, but I'm not totally sure. Repeating the entire computation.
So they're asking if it would be simpler than just doing error correction, or can we combine both error correction and repetition to get more accuracy?
So repetition will help you for really small systems. But what happens if you don't do error correction in a quantum computer, which is a bigger system, is the probability of it failing will be almost exactly 1. So it will almost certainly fail. And the probability of it failing with the size of the computation goes to 1 exponentially quickly. So you would need an exponential number of copies of the system in order to extract the output. So the answer is that won't work for a big quantum computer. For a really, really small quantum computer where you'll be in the regime where just 1 error might have occurred, then you might be fine. But remember, just to give a rough idea, the number of gates that you're going to need to apply in, say, Shor's algorithm is going to be around 10 to the 15. And so if each of your qubits is failing with a probability 10 to the minus 3, then there are going to be like 10 to the 12 failures in your overall computation. So the overall computation will definitely fail if you don't do error correction. And it's not that you can just repeat over and over again. You would need to repeat it many billions of times.
And Mike asked, also in terms of quantum error correction and reducing noise, is this still only over cables, or is there a less noisy wireless method?
There's noise. So there's noise in the sources of the noise I didn't really discuss today, because they come from really everything. So for example, noise includes noise on the cables, but noise also includes a photon which happens to hit the system. Noise includes the fact that other qubits are nearby the qubit that I'm considering right now, and so they interact slightly. All of these effects will introduce noise, and they're unavoidable. You can't reduce the probability of noise to be below a certain level. It's just practically never going to be possible. So you have to accept that there's always going to be some noise.
Yeah, and I think there are some people who are thinking more about communication, like what type of cables, optical, electrical, or even someone said gamma waves. I think they're more thinking about how you're transmitting the data and the errors occurring there.
Yeah, and that's a separate topic, but in this case, we're really just imagining you have a quantum computer, it's sitting in one place, and you want to use it, and errors happen while you're using it. Yeah,
and we're talking about the actual qubits that's itself generating errors.
Yeah.
So yeah, less about how do you transmit information. It's more about your actual qubit, for example, superconducting qubit sitting in a really cold dilution refrigerator.
Both the noise could be on the superconducting qubit itself because there's some changing magnetic field which is affecting the qubit, or it could be whenever you're reading out the information from that qubit, then the wire has some noise and you get the outcome wrong. It can be all of these things, but there are many, many different sources of the noise.
Yep. Brandon says, are there any error mitigation techniques other than error correction that are promising for working in conjunction with error correcting code to achieve fault tolerance?
Yeah, I would say that everything, every approach has some error mitigation techniques. So, for example, in superconducting qubits, and you've probably been through this, you can tune the system so that it picks up noise less. There are many things that people do at the physical level to try dynamic decoupling in some approaches, but various different physical things that you can do in your hardware to reduce the noise. And there you can think of those as helping error correction by reducing the probability of a failure of each component. Yeah, so yes, I would say that's very important, and making the probability of each operation in hardware fail as small as possible is extremely useful for reducing the overhead of quantum error correction.
Yeah, and we're at time. I think, yeah, we should let Michael go back to his day. Thank you so much for joining us. And also this class is really to show people what's in the real world. Like in the past, maybe 20 sessions, we're like learning the basics of how quantum computing works, and then writing the code, and perhaps you can run on simulators, which runs perfectly, and there's no like physical real world errors introduced. But today we see that there's a lot to consider and it's very difficult, but there are ways people are working on it. And I think error correction is actually one of the really needed area for quantum development, quantum computing. So for the audience here, if you are entering the field of quantum computing, this would definitely be a very needing area that we need a lot of people to come together and come up with new methods.
For sure, yeah, I think it's a very exciting research area with huge potential impact. And yeah, you should definitely, if you want to learn more, then you should definitely feel motivated to do so. There's a lot of cool research being done.
Yeah,
thanks
and
everybody.
Like small colleagues. Yeah. Thanks everyone for joining, and thank you for coming to the very last class for 2020. So we may have new contents next year. We'll keep everyone updated through the Hackaday page, and also check out our Microsoft websites. All right, thank you everyone.
Bye.
Thank you, Michael. Have a good day.